With our Unit 10 review, this is the one that, at least for a lot of students, might have been where it got the most complex, the most complicated, and maybe where you did the worst. I don't know, but not necessarily for everyone here. This is going to be inference test for two samples, and that includes the confidence intervals and the hypothesis tests. So what makes this a little bit more complex is that now we've got these more complex standard errors to work with. There are some different criteria for checking your conditions, and there's just some weird things like right here when we have an inference test, a hypothesis test that is, for a difference of two sample proportions, well, then we pool it. We pool our proportions into a p hat sub c. And when it's a confidence interval with a difference of two sample proportions, we don't pool it. We keep those separate. So just these weird nuances that are hard to keep straight. And besides that, once you can plug the stuff in, there's a chance that you plug something in incorrectly. But anyways, that's the basic idea. Now, it's nice and easy to summarize this chapter just with one thing, which says you're either going to do a hypothesis test or confidence interval, and you're going to use this information. But of course, we know the reality gets a little bit messier. So let's look at, let's just go ahead and start with this one. I'll let you guys try this one on for size. With this particular problem, we have two samples that were sent out. We have a sample of 500 coupons for $1,000 off and a sample of 400 for 3% off. The question of interest here is, which will bring in more customers? Or specifically, will a flat discount bring in more customers than a percent discount? Which is a good question to ask. Now, the answer to this is how many out of the 500 coupons came in for a flat discount compared to how many out of 400 came in for a 3% off coupon. And we're essentially looking at counts. So when you have a count out of 500 and a count out of 400, that's two proportions. So you're going to end up with p hat sub 1 and p hat sub 2 for the two different types of coupons, and we want to get the difference between those. So this is actually going to be a two-sample z-test for a difference between two proportions. All right. And it's easy to get these mixed up, but you just have to ask yourself, when you're talking about proportions versus means, is this data something that I would get an average of, or am I looking at counts? And in this case, hopefully you can convince yourself at this point that we're looking at counts, not getting an average of data points. Okay. All right, try this one. Well, I got a lot of responses, and the good thing is every one of you came to the same conclusion, that the answer is E, and that is correct. It is going to be a two-sample Z interval. The difference between B and E is that where it's the difference between population proportions. So there it is. And frequently the word population isn't even part of it. You can just say difference between proportions, but it is understood that we're inferring about the population. Okay, so let's go ahead and move ahead with that. Okay, another conceptual one here. I'm going to let you guys give this your best shot. So this is, these are the kinds of questions that can drive me insane, and they can probably drive you guys just as insane as me, because some of them is like, oh, I know it's not this, I know it's not this, but is it that or that? And you just go back and forth. With those kinds of questions, just test strategy, coin flip. If you can narrow it down to two choices, you got a 50-50 shot, right? But let's kind of see in this particular scenario what would be the best answer. So they describe the scenario, the experiment, where it's people who slept for either 8 hours or 6 hours, and then they take a test, a memory test, and then what proportion of them were able to pass the memory test. So if the amount of sleep had no effect whatsoever, which of the following experimental results would be anticipated? So they're going to subtract one result from the other. So we are looking at a difference of proportions. So the p-value is significant if it's less than 0.05. But if it's greater than 0.05, which will happen 95% of the, well, let's talk about that more. But if it's greater than 0.05, we fail to reject it. Now, imagine we did this experiment over and over and over again. We're imagining that there really is no effect of sleep on passing this memory test, but just by random chance, there will be times where your results end up in that 0.05 range. So by random chance, you will get some statistically significant results, 1 in 20 times. But most of the time, they're going to end up in this range right here. So 95% of our experiments should have a p-value greater than 0.05. All right. So 1 is good. So I can cross out these two. So I've already been able to narrow it down. At this point, at least it's a 33% chance of getting it right. So with the second one, there will be about an equal number of experiments showing positive and negative values of drug effects. Same thing as before. If I do a bunch of experiments and we're assuming that there is no effect, if there really is no effect, then just random sampling, sometimes I'm going to get one of the values slightly higher than the other. And then it might end up being a positive value. So here's one sample result. But then the next experiment that I do, I get the other value is slightly, the first value is slightly lower than the other. So then I get a negative experimental result. And I can do this over and over again. Now, a lot of them will be positive values, a lot of them will be negative values. But if there really is no effect, then we should see about 50% of them being positive and 50% of them being negative, hovering around 0. So this is an accurate thing. So that one's good, that one's good. So I can go ahead and cross that out as well. So the question is the third one also accurate? Okay, so I will cross these three out. When 95% confidence intervals for the population drug effect are constructed, these confidence intervals include 0 about 95% of the time. So remember, confidence level, 95% confidence level means that with repeated confidence intervals, we should capture the true population parameter, in this case, difference in population proportions, 95% of the time. So if there is no effect, that means 0 effect. Then remember we had that experiment where, we have the true, not experiment, it's the visualization of it that showed here's a confidence interval that captures the true mean. Here's another one that captures the true mean. Here's one that captures the true mean, and so on. And all this, but then every once in a while you're going to get one that just barely doesn't capture it. So this one doesn't. But then the next one does. And then, maybe you had another one up here that captured it. So out of 100 confidence intervals created, if there really is 0 effect, then we would expect 95% of our confidence intervals to capture 0. So this one is also correct. So the best answer is B. Okay. That's some good old-fashioned review of some conceptual ideas, some conceptual things that are easy to forget. All right, let's try another one. Now, this is one that I'll admit I read it, I answered the question, then I was like, wait, did I read that right? And I went back and luckily I did, but that was a good lesson for me. Make sure I read this more than once to make sure I really know what's going on. So we are definitely looking at a difference in mean between two different models of laptops. And so this is a confidence interval, a two sample T interval for a difference in means. And that part is pretty straightforward. Or that part we can be confident about. So now what happens if we did the same test over and over and created different confidence intervals each time. We're not going to get the same confidence interval every single time we do it. So, there's a number of these we can rule out, but essentially, I'll just jump to the answer. The answer is C. So there is a true difference. If we could take every single laptop and drop them until they no longer function and figure out the true difference, then we could find what the true number is. Of course, that would make no sense to do in the real world since we want most of these laptops to be sold. So we would infer from this that approximately 90% of the intervals that we constructed will capture the true population difference in means. Okay, so that's the idea behind that. So this, you'll notice, before we jump into this one, you'll notice that a lot of these have not required calculations. And I know I've made that point a few times, but you can definitely see it. So look at this question. This one will require a little bit of calculation, but I'll give you some time to work on that. With this particular problem, even though it gives us a lot of numbers, if you look at what we're asking for, what they're asking for, it's a standard error. And so the standard error is given by this formula right here. You take this sample standard deviation of your first sample squared divided by n, plus the sample standard deviation of your second squared divided by n. And that is it. And you can find that here for standard error right there. And that should say n sub 1 and it's n sub 2, so I forgot to add that. So all I need to do is look in here and find, for the first sample, what's the standard deviation of the sample. So in the first one, it's 1.6, so 1.6 squared divided by 195 in the sample. And then the second one will be 2.1 squared divided by 143. And there you have it. When you do this math, what I got was 0.2097. And that's what, of the people who answered, most of them said that. If I made an error in calculation, we can find that. But 0.2097 is what I came up with. At the very least, you can see what the correct process here should be. All right, and as we go through, if there are some you have questions on or you just want to kind of make a special note on, like this is something I have forgotten, I want to make sure and go back and look at this, then you can do that. And when I say you want to go back and look at it, that might mean, well, this is unit 10, so you can go back and you can find the homework assignments that you had during that time period, or you could go back and find some of the problems in the unit 10 module. And speaking of modules, I did open up all the previous tests for you guys to go back and look at to see what the correct answers are. So I would highly recommend looking through that this week, since your final will be on Friday. Look over all the old tests to get a reminder of what your tests are going to look like. All right, now enough about that. I think there we go. This is the last one for unit 10, and I will let you guys look at this one. So this is, like I was saying, definitely a more time-consuming problem. In fact, I gave you guys over 5 minutes to try this one. Now, I will show you kind of the way that we've been doing it. I have intentionally not shown you how to do this stuff on the calculator, maybe to a fault. In a regular school year, maybe we would have had more time to learn both methods using the calculator and without, because, well, I'll jump into that in a second. Now, the way you do this by hand is that we're doing a two-sample t-test. So I'm trying to find a t-statistic using my x bar sub 1 minus x bar sub 2. And of course, that's minus mu sub 1 minus mu sub 2. Okay, I can't really, right in the corner, there it is. And then this is going to be over the square root of s sub 1 squared divided by n sub 1 plus s sub 2 squared over n sub 2. Now, when I plug stuff in here, it's going to be 51,472. Don't want to do that. Minus 49,006. And then divide that by, well, if I do all this down at the bottom, these are a bunch of numbers. I get it, but 62,074 squared over 117 plus 9,319 squared over 78. And these are numbers I'm getting from this. I can do all that on the calculator, get a t-score of 2.048. And then from there, the last thing I need to do is a t-CDF calculation going from 2.048 to positive infinity with 77 degrees of freedom. And from there, it will give me, because 78, so I just take 78 minus 1 to get my degrees of freedom. And I'm going to get a p-value of 0.0219 or something like that. I believe that's it. So that is time consuming to think of the formula, to plug the numbers in, to do all that. But if you can go quickly on some of these conceptual questions, and some of you were taking just like less than 30 seconds on some questions earlier, so you can spend 5 minutes on a question if you really had to. Okay, and so here, yes, this would be significant at 0.05, but not at 0.01. That is the correct answer. Maybe I should show you guys real quick. And again, I know this is maybe a little late, but if it's a multiple choice question, you don't have to show all your work. So why do it the longer way? So the easiest way to do this quickly is if you do stat, and then you go over to your calc, and then you go down, you're going to see your 2-sample t-test, which is option 4. And you don't have to necessarily do this, follow along, but if you look real quick on my screen, you'll see that I have all the data from this particular problem plugged in. So hopefully that's showing up correctly. It's reversed on my screen, but I don't know if it's reversed on your screen as well. But if you look, you can see all the data, 51,472, 49,006, and then all the anyways right there. The only thing right here is you have to determine, we had a specific hypothesis that District 4 made more money than District 7. So that meant mu sub 1 would be greater than mu sub 2. We never pool, but then we can just calculate. And notice, just all I have to do is plug the data in, and I can get my p-value right there, 0.02134. So we came really close to that with what we did. But notice the the degrees of freedom on this is like, there you can see 123.1. Yeah, we use 77 as our degrees of freedom. So there is the way of doing that, and especially for those of you doing the AP test, maybe that's something that if you want to, we can maybe sit and we can look at that and go through how to do things on the calculator a little faster. But there we are, 2 ways of getting the answer, one of them faster than the other. Okay, that is unit 10. That's the big one. Unit 11 is all about chi-square. And I'm not saying chi-square is easy, but I think the unit 10 stuff is definitely the most time-consuming stuff that we've had to do, because the nice thing about chi-square tests is that the calculator takes care of it all. So we are comparing distribution to count. So we can do the chi-square goodness of fit test to see if one sample matches what we expect. The chi-square test of homogeneity to see if 2 samples match each other. And the chi-square test of independence says that if one sample that has 2 variables, if the 2 variables have an association with each other. The expected counts, remember your expected counts for your goodness of fit is just going to be the variable, the count, the total number in the sample multiplied by the probability of each category. Okay, and well, maybe I'm not breaking that down clearly enough, but the more specifically with your expected counts on homogeneity and independence, it would be, if you have a 2-way table, looks like this, it would be your row total times your column total. For this one, the expected value would be those two multiplied divided by the table total. We have some posters, the reference posters in the Canvas, so that might be something that you want to review. This is just supposed to give you a heads up on like, hey, remember these things. Okay, we do not calculate chi-square test statistics by hand. That would be very time consuming. And you set up a list or two matrices, and then you let the calculator handle it from there. And of course, knowing that we don't do this by hand, it's unlikely you're going to get a test where you have to even calculate this, because like I keep saying, AP sets this up where technically you can take the test without a calculator. Okay, so there are conditions that are associated. This first question is dealing with conditions. I'll let you guys have a look at that. Okay, we are just checking conditions for the chi-square test for independence. And one thing we have to remember about the chi-square test for independence is that the way that this is conducted is we take one sample split into two variables. And we want to see within that one sample, are these two variables independent of each other? Meaning, is there no association between them, or is there an association and therefore they would not be independent? So the conditions here are the same as for most of our other tests. Is it random? Is it is it less than 10% of the population or independent? And this is a weird thing. Let me come back to that one. And then we could essentially say, is it normal? But really, is it large counts? Do we have a sufficient amount in each category? So the only thing here is that our smallest cell has to have at least 5. And so that is the case, definitely. We can see the smallest count right here is 148.5. So we met this one. It says it's a simple random sample. We've met this one. And this is not, these are not independent observations. So we need to check the 10%, and it has been met. Now, the independence here is, we need to kind of think of them separately. We're saying that each trial, each person that has been included, does that change the probability that the next person will be included? Well, yes, it does, minutely, because we're sampling without replacement. So these are not independent as far as being included in the sample. And that's when we're going back to sampling methods. So in that case, we need to check 10%. But if this is something dealing with independent events like rolling dice or something like that, then we would just be able to say, oh, they're independent from each other. Now, in this case, yeah, we check the 10% condition. So bottom line, the answer is E. All of them have been met. Okay. And I apologize if that was confusing, but here we go. Another question. So this one does require a little bit of calculation on your part. Okay. This kind of question is one that, like I keep saying, where that you can theoretically take this test without a calculator. You can calculate this chi-square stat and the p-value and all that fun stuff by hand, but it would not be, this would be one that I would have someone save till the very end and just try and finish it with what time they had. With a calculator, it's not so bad. All we have to do is figure out our two matrices, plug this in for matrix number 1, figure out the expected counts, which would be, again, for this cell, it'd be 200 times 201 divided by 404. So that would be the expected count for that cell. And then you just have to go through for all of them, figure out what the expected count would be. And once you have that, you can just do your chi-square test on your calculator. And you're all good to go once you have the matrices set up. And the answer is B. All right, so if you have a question on that one, please let me know. But that's some good old-fashioned calculator work. Let me see how many more of these I have. I have quite what is that? 1, 2, 3. Yeah, I have 3 more. This is a good one right here. This shouldn't take as long. With this one, this is actually, compared to some of the other stuff at least, an easier question. The only reason that the reason I brought this one up is because it's important to note that you can have decimal amounts in your expected counts. In your observed counts, it has to be whole numbers, but in your expected counts, it can be decimals. So and everyone answered D, which is correct. But if you thought it was that one right there because you rounded, then I just wanted to make sure you guys knew that decimals are okay in expected counts. So, and really the way we did this, and just in case someone was confused even beyond that, since there are 230 in our sample size right here, I just take 230 and I multiply that number by all these different proportions. So 230 times 61%, 230 times 22%, and so on, and you get all your expected counts. All right, let's look at this real quick. With this one, there's maybe what we can look at. Let me give you the answer first of all. The answer is B. The p-value cannot be determined because we don't know the sample size. And let me show you what we could do if we did know the sample size. If we knew the sample size, we could figure out the degrees of freedom. And then from degrees of freedom, we could come over here to our chi-square table, and we could go to the correct degrees of freedom, find where that chi-square statistic is. So let's pretend that there were 3 degrees of freedom. And so if you're looking at this, 3 degrees of freedom, you can find 6.25 somewhere. I can't quite see it. I think it's right there. It's the 4th one over. Okay, so it's right about here. All right, 6.25. So that tells me that at 6.25, that is statistically significant at the 0.10 significance level. Okay, now that can allow us to estimate roughly what our p-value is. If it fell in between 2 values, we could kind of say, well, it's between these 2 values, so it's between those 2 tail probabilities up at the top. So that's dependent on us knowing the sample size, but without that, we can't do anything, and so we just have to say, well, nothing we can do here. That's great that chi-square statistic exists, but it doesn't do us any good. Okay, so let me go ahead and look. I believe there's just one more question. Oh, never mind. How about, oh, wait, no, there was one more. I lied. Okay, so here it is. Go ahead and see if you can answer this one. The degrees of freedom for a chi-square goodness of fit test. This is actually a pretty straightforward calculation. And what it is it's your degrees of freedom equals your number of categories minus 1. Not the sample size, but the degrees of the number of categories. So if we have 1, 2, 3, 4 categories, and it's not the number of days because they actually have 4 categories because Monday through Thursday is 1 category. Friday, Saturday, and Sunday are each their own. So 4 categories minus 1 gives us 3 degrees of freedom. And the answer is B, or that answer right there. Now, it's worth talking about for just a second that if it was a if it was an independence or homogeneity test, then your degrees of freedom equals your number of rows minus 1 times the number of columns minus 1. Only within the body of the 2A table, not including the margins. So that is the degree of freedom calculation there. You have all your references. I highly encourage you to go back and review that stuff as well. You will have Unit 11 questions on your final. Look back over this stuff, and yeah, let me go ahead and clear that out. Here's what we've got. I assigned a couple more FRQs. Give that a shot. If you haven't looked at the Unit 9 FRQ, I highly encourage you to do so, especially if you're taking the AP test. And remember, it is all optional whether you do it or not, but we will take some class time to go over some important things to know. All right, with that, have a wonderful day. I will see you tomorrow. And yep, have a good one.